Okay, we'll begin so we can preserve time. Um, I think what the first two lectures and what Reza is going to go over is going to be very useful because in the afternoon we're going to have a CrowdSpark tutorial and all these concepts will come flooding into your mind and then you'll have a ton of questions and that'll be great because you can put everything into practice. So Reza is coming from City College, not too far away from here, from the Center of Discovery and Innovation. I asked Reza what he would have done if he wasn't doing science. He would still be doing science, but he'd be a science philanthropist. Of course, I don't know how that works, but he'll just be able to just freely outreach and train people.
Yeah.
Okay, so I'll let you take it away.
All right, so you can hear me, right? Yeah, I sound weird. Okay, so thank you so much for allowing me to do this. And I'm a little tired because I just came from another hour-and-a-half lecture talking about nucleotide synthesis and all this biochem 2 stuff. So this is, I have to say, this is a lot more enjoyable for me to talk about because it's what I do. I don't do anything on nucleotide synthesis, no heme synthesis, so all that stuff is, God, I hope this kid isn't smarter than me. So, so here you could be smarter than me, but at least I know a little bit about what I'm talking about here. Okay, so rather than making this into a lecture, let's make this more into a discussion. If you have any questions, let me know. I cannot cover everything that there's out there. I mean, I was just sitting there, I'm like, oh geez, I forgot about this, I forgot about that. There's a couple programs I'm not giving shout outs to, if that's what you want to call it, but there's a lot of different programs out there. I think some people say you should master one and be the master of it. I think you should try to learn all of them. They exist because each one has something unique. If they all did the same exact thing, why would they exist, right? So you can go, oh, I want to do this program has it, oh, I want to do that. I have a particular pipeline. I'll talk about what that pipeline is. The reason why I do that is because it ends up being the fastest. It's really flexible. But you might say, no, I don't like his stuff. I don't like doing it his way. I'll do it that way. So let's keep it a discussion. There's not going to be, I heard algorithms. Unfortunately, there's no algorithms here for you. So if you were looking forward to that, I'm sorry. You can ask Fred more questions. So let's begin. It's going to be more like a practicum. I'll talk about how I do it, and you guys can pick my brain until I have none left. Okay? So this is essentially the flow chart of what we do, right? And you have to think about every step, right? Data collection, what magnification do you want? More importantly, what pixel size do you want? Do you want super resolution? Do you want counting mode, integration mode? And the folks here at NYSPC will help you out with that, right? So I've collected a bunch of data sets. I still go and go, what's the newest and latest? And when directed electron detectors came out, there was about 5 different ways of doing it. And I come from a background of X-ray crystallography, and back then, there was like 5 different ways of doing it, and at the end, everything converged into a single way because all 5 of them worked. And a variant of all 5 of them ended up being the fastest. So things have converged, and there's really one way of doing it, but you can still deviate from that. And the folks here at NYSPC keep up with that. So I ask them, what's the latest and greatest, what's the best way of doing it? And then we can go, depending on the project, we can fine-tune the data collection strategy. The frame alignments, I'll talk a little bit about that as well, but a lot of the frame alignment is done here as well, right? Because as it's coming off, you can align the frame so when you get home, you can start processing the data and you can do particle polishing at the very end. So frame alignment is not so much of an issue. Then after frames, you have to identify the particles, use CTF estimation. You can do CTF estimation here, or you can do it again at home. Particle extraction, CTF correction, sorting particles. I don't sort particles anymore. I go straight into 2D classification. There are deviations from this, and I'll talk about what that deviation is and why you'd want to do it. Generate your model, ab initio model, which is generally how most individuals do it, although I'll spend one slide talking about alternative ways. 3D classification predominantly to clean up the proteins, to get rid of bad particles. And then I also use it for getting out some heterogeneity of the structures, maybe that's me again repeating 3D classification I use for cleaning up particles. And then you improve the resolution, you polish the particles. There's an iterative process of CTF refinement, particle polishing, CTF refinement, particle polishing, and you do this as, you know, like it's like if you've done X-ray crystallography, if you come from a background of X-ray crystallography, when do you stop refining? Well, when you're sick and tired of it, right? And that's when you stop doing it here. You can watch the resolution and you reach a point where you go, okay, I'm getting a 0.2 angstrom improvement, and it took me 3 days to get here. Do I want to go to another 0.2 angstroms from another 3 days? Is it going to improve my story? Is it not going to improve my story? If it is, then you do it. If it's not, then you say it's just not worthwhile, right? And then you can do additional types of variance map, B-factor plot, focus classification. Then you go into your model building and refinement, okay? So, any questions so far? All right, so this is the workflow I use in CryoSpark. So when I start, I go straight into CryoSpark. Why? It's fast, and I get immediate readout of what's going on, right? And everything is put into a GUI format, so taking notes becomes really easy. Now, you can take notes on CryoSpark. It gives you little windows that you can put your little notes into, but the problem with that and the difference you have to realize between you and myself is that, number one, I've done this many times. I know where problems can go. And number two, this particular project is something we've worked on for quite some time. So that's why the workflow looks so nice. Generally, it'd be a huge mess, right? It's like 1,000 jobs. Here's 1,001 jobs. What happened where? I don't know what happened in job 95, 95, 958. What happened in job 621? So CryoSpark, because everything is there and I can just do that on my computer, I can just do screen grabs, put it into Microsoft Word, have them right next to each other and keep really nice notes about what's going on. Because at some point, you know, when you start writing or when you start working on a second project or you're working on something else, you come back to the workflow and you go, oh my God, what the hell happened? I know I had to do something 4 or 5 times to get it to work. I can't follow it. Do I start from scratch again? But you know that's the last thing you want to do because you're going to hit the same exact problem again. So because CryoSpark puts everything easy for taking notes, that's another reason. I just put it into Microsoft Word, I come back to it, and then I look and I catch up with what I did, where I left things off, what went wrong, what I need to focus on next. So that's why I go into CryoSpark. And then after I'm done with CryoSpark, then I can take the data, take the particles, or take the coordinates, and then I can fork off into whatever direction I want. I can go into Relion, I can go into CryoDragon, I can go into anything I want, right? But the efficiency and the rapid response that I get from CryoSpark is the primary reason, and taking notes is why I start off with CryoSpark, okay? Any questions? All right, so what's in the pipeline? So as the images are coming off, you want to do motion correction. Now, motion correction, there's multiple programs out there. So there's UCF Motion Core, which I took off because no one really uses it anymore. There's Motion Core 2, which is quite popular. It's used here predominantly. What Motion Core 2 shows well, I'll get to that. There's also Unblur, which is Nico Grigoriev's algorithm. There's Warp, has its own algorithm, and there's also CryoSpark. So all of these provide programs for doing motion correction. What is motion correction? So when you expose your specimen to a beam of electrons, what happens is that your particles move, right? They move and they rotate. And this moving is going to blur the image and it's going to impede your high resolution. You're not going to be able to high resolution. Maybe you'll get to 5 angstroms or such, but you need to correct for this motion, and you can correct by this motion for simply collecting many images very rapidly. You collect the movie of a running horse, you can align the horse and get a nice picture of it being still. And those legs aren't so blurry anymore. Now you can see what the legs look like. So that's what motion correction does, is it aligns all the images it selects one image and aligns everything to it, and now you have an aligned image. And now you have a more sharper image. So on the left-hand side, This comes from Melanie Campbell's paper in 2012. I believe this was the first example where motion correction was done. It was done with Niko Grigoriev. The sample is rotavirus. On the left-hand side is the uncorrected image, and on the right-hand side is the corrected image. And when you start looking at the spikes, these protrusions, you can start seeing a little bit more detail with your eyes, right? And on the right-hand side, you have the power spectrum. This is the average. This is the actual power spectrum, and this is what CTF find fits to it, right? And here you can see that the experimental image, experimental CTF, after drift correction has been applied, you can see more tone rings, right? Because you're seeing more spatial frequency. And now your CTF fit is better, your alignments will be better going down the pipeline, and you're going to get to a higher resolution. Motion Core 2 builds on, so on Blur, everything, all the frames are treated as the entire frame is aligned as a rigid body. In Motion Core 2, you can treat the entire frame as a rigid body, or you can break it down to little patches, right? You can say 5 patches in column, and then 5 rows. So each patch will be aligned itself. So this way, you can get a better alignment. So because what's really happening is that each particle is moving in a different direction. And so if you align the entire thing, while one particle will look good, the other one may actually get more blurry. So you want to break it into patches. Ideally, you want to break it into as many patches as possible, but then that's not possible because then your signal is lost. If you imagine your patch is 1 pixel size, how are you going to align a pixel, right? So if you go to the extreme, it doesn't work. And if you make it 1 micrograph, then that's also going to be problematic because it's just treating the entire thing as a rigid body would not give you as much of an improvement as you can get.
Would that mean that if you have a very dense, or if you have a lot of particles in
Yeah.
the frame, it would be better to do smaller patches than if you have less dense particles, you can get away with zooming good data larger.
So good question. So I've tested this and others have tested it as well. And I've seen that a patch, if you go smaller than a patch size of 5, depending on how much sample you have on there, the alignment doesn't work as well anymore, right? So I always do a patch size of 5. And it works with small particles, it works with larger particles. It may not be the best solution, but remember, you have particle polishing at the very end, right? So with the particle polishing, and that goes on, you do this, the alignment on a per particle basis. And you can't do better than that, okay? So I always start with a patch size of 5. Other questions? Yes?
The frame alignment, is it doing similar cross-correlation?
It's cross-correlation, yes, yeah. Yeah. So with Motion Core 2, it allows you, so not only are you doing the X and Y, it also models for this buckling effect that you see with particles. So it fits the whole thing to an X squared function, so you get an additional degrees of freedom in there that improves the alignment a little bit more. Okay. Yes. That's particle, yeah. So yeah, that's done with the particle polishing, and the reference comes from your experimental data. And yeah, so if you can't do that at this stage, because if you start with a new sample, you have no reference, right? So yeah, that's done later. I saw a hand back there, yes. Is there a question? Okay, no question, all right.
I do have a question.
Yes.
When you upload your movies, you can add the reference into it, right?
You're talking about the gain reference correction. Yeah.
So that's different.
Oh yeah, that's a camera correction, right? Because you're going to have, as with any camera, you're going to have dead pixels, right? You're going to have pixels that are always black or pixels that are always white, and you have to get rid of these. Because if you don't, all your algorithms are going to align onto those because they're so strong. I mean, it's either if it's an 8-bit, it's all either 256 255, or it's 0. So everything's going to align to that. So that's the gain reference correction that you have to do. And then on top of that, these cameras are manufactured. It's not magic. So they're going to have other problems. They polish it. And if you see a gain reference, you'll see that it's got these swirls on it. And the swirls is from the polishing that they use an orbital and they polish it, right? So you have to subtract that out of the image too, or else you're going to have these rings running through all your, and everything's going to align onto those. Yes?
Gain correction on those cameras, it's a manufactured defect. Does that change over time? Do you find like when you're doing like experiments and stuff like that?
Yeah.
You take the gain correction measurement every single experiment, right? Is that
So,
pass it along?
You know, I think that's a question best asked for NYSPC, but I've asked a similar question. Gain correction is generally done every time the camera is taken out and put back in, right? In case something might happen. And I've heard of individuals doing this for every experiment. It ends up being you use it a lot of times, and it's not necessary. But superstition is hard to break, so I don't want to start getting into superstition.
Thank you.
Yes.
Motion correction, is there any parameter the user can tweak to get better alignments?
Sure, there's a B factor you can put in, and what the B factor does is it's like a negative temperature factor correction in X-ray crystallography and EM. It upweights your high resolution terms. You could put that in. That's one. The second one is patch, and then I think the number of patches you want to give it, and I think the third one is the number of iterations you want to run until you have an acceptance. Okay. Other questions? Okay. So then, after you've done your correction, then you want to do your CTF correction. And if you look at your micrographs, if you are collecting data here, you'll see 3 micrographs of high resolution micrographs being generated. One is ENN, one is ENN-A, and then one is ENN-ADW, right? So during the motion correction, you can also apply a dose weighting scheme, right? So you know that you don't want to shoot your specimen, or you don't want to use data where you have more than 20 electrons per angstrom squared being exposed to your specimen, because after that the specimen starts falling apart due to radiation damage, covalent bonds breaking and such. So you can do a dose weighting, but when you collect data, you want to collect with a lot of exposure so your signal is increased and you can get a good CTF value. Right. So you can, for example, do an exposure with 54 electrons per angstrom squared, and then you can apply this dose weighting strategy to it, whereas the later frames get less weight applied to them, and then this will allow you to use as much of the data as possible without having to worry about radiation damage. So that's done during this motion core process. And so when you collect data here, and you can do this, you can set this up however you want, is you will have a micrograph that is just a raw micrograph, that is the average of all the frames, not motion corrected. You'll have one that does not have the dose weight applied to it, and you have one that has the dose weight applied to it. And if you look at the frame aligned and the unaligned power spectra, you'll see a lot more tone rings in the motion corrected, right? And you'll see a little bit of difference between the dose weighted and the non-dose weighted. But point being is that when you, in this comes from CTF find, this is the average of the experimental power spectrum, and this is the fit. And as you can see, these tone rings go out beautifully, right? And this is what happens when you do your motion correction. When you don't do motion correction, they tend to die maybe around 7 angstroms or 6 angstroms, okay? So you do your CTF correction. There's a lot of different CTF estimation programs out there. One of the first ones that did it automatically was ACE Automated CTF Estimation. There's CTF Find 4, Sparks and EMAN have their own algorithm. There's GCTF, WARP, CryoSpark, right? Which one you choose, it's a personal decision. I do, like I said, I start off with CryoSpark, and I use the values in CryoSpark. So here is the power spectrum. This is an output that you get from CTF Find 4. This is showing you the 1D profile with the fit. This is an output from CryoSpark. Again, I can put this into my notebook saying this is typical. I don't have to generate it. Like CTF Find 4 does generate it, but it generates a PostScript form. I have to convert it to PNG, bring it out. Here I copy and paste, right? It's much easier to do. And then what CryoSpark also, what I like with that is that it provides what's called a patch method. So it estimates a CTF for each patch on the micrograph, right? Why would you want to do this? Well, you might want to do this particularly if your specimen is tilted, right? If your specimen is tilted, then your CTF value at one point is going to be vastly different than at the other, and you don't want to use the average CTF value for the entire thing. The other advantage is that when you have an ice layer, you're going to have particles near the top, you're going to have particles near the bottom, and you're going to have in the middle and near the bottom. So each particle is really going to have its own defocus value. So by using the patch method, you're getting closer to the true defocus value of the particle. Okay, so I have particle orientation problems with every data set that I have, so I just collect tilted. Everything's at 45 degrees tilt, right? There's a lot of again, there used to be the story that, oh, you can only tilt if you have a gold grid. If you don't have a gold grid, it's not going to go to high resolution. You're wasting your time. It's not true, right? You can use a gold grid. That's fantastic, but you don't need to use a gold grid. I've used regular carbon-coated grids where you have carbon on there, grids where you don't have carbon on there. Drift is not a problem, okay? So each project is going to be different, right? If you want to test it, you got to test on 100 different samples and say, okay, it works 90% of the time, but that's what it is. So I always collect it tilted, and I need this patch method. And what the patch method also shows you is that it shows you that, yeah, your grid is tilted because the focus value at this point is different than the focus value at this point. Right? So you can look at this, and if it looks like a plane, you go, okay. If it looks like, if it's hyperbolic or it looks like an x cubed kind of a function, you go, something's going on. And you look at the image and it's black, it's completely dark, there's no signal. You go, yeah, these are just garbage things that are doing that. So, so that's one of the advantages with using CryoSpark. Yes?
When collecting the data sets, you have the unaligned, the aligned, and the dose weighted.
Yes.
So do we need to run motion correction on the dose weighted or just do that identity estimation?
Okay, so the dose weighted, it does dose weighting after it does the alignment. So at this point, I only analyze the aligned images, right? So what you can do is you can do your CTF estimation on your aligned, not dose weighted. This way you get more signal and your CTF estimation is better. And then the remaining of you can pick particles on those as well, but you extract and everything you process is on the dose weighted material, right? So that's the strategy that I use. Now I've stopped, now because this requires, I used to use the non-dose weighted micrograph, but I've stopped using it because it becomes too much to juggle, right? Myself doing it, because of my experience, it's doable, but when you try to teach someone and in the beginning they're confused, I have 3 images, why am I using 3 different things? It becomes a little hectic in the training aspect of it. But after they've done it a couple times, they go, why didn't I do it the other way around? It's better, right? And they try to push the resolution. So do it, it depends on how you, if you like to tinker with data, then I'll just leave it up to you. Okay, does that answer your question? Any other questions? Yes.
So the spatial frequencies, like of the CTF plot there.
Yes.
Like, you can, I guess, kind of use that to say, I have more higher spatial frequency
Yes.
information, so
Yes.
it should go to the higher resolution.
Yes.
How much can you trust that? Like, if you have those rings at like 2 angstroms, how well does that correlate to like a 2 angstrom?
So I like to look at things in extremes, like a mathematical equation, take it to the extreme, take the limit to infinity. You can have a beautiful power spectra and absolutely garbage data. When you shoot over carbon and there's no particles there, right? And remember, your grid has carbon on it. And the microscope isn't going to be perfectly on each and every time. So if you have small particles and the microscope ends up shooting over carbon, then you'll get a beautiful power spectrum. But those particles are useless, right? So this comes in the curation part. You can't use one metric for everything. What I like to use is I like to use multiple metrics. Multiple metrics. And I'll talk about that in a slide to come. Okay, questions, very good question. Okay, so the next thing, before we get to that, it's particle picking, right? Because why? Because particle picking is another metric I like to use, and I'll give you an example of why. Many different ways to picking particles. I've written at the very top, going in a chronological order. In the very beginning, we did things manually. I love doing things manually, right? But that was before you can collect 10,000 micrographs in one data session and more, because you can't go through 10,000. So first it was manual picking, then it was blob picking, where they did difference of Gaussian. You did a low-pass filter, you identified where these blobs were, and you picked the blobs based on the size. Then came template picking. If you have a template, you generate references, you low-pass filter those references, and you use the templates to pick particles from your micrograph. And then came the magic of neural network. Now, to Fred, it's not magic. To me, it's magic. Okay, and now you train it on a particular data set, and it doesn't need to be the data set that you collect. They have generic data sets that it's been trained on, and you just pick with that, and then you can get your particles, go back, retrain, and pick again. Okay? And I'll go through that in a slide. But on the left-hand side are some of the particles, some of the programs that do this stuff. Again, I've missed a whole bunch. Find EM, Dog Picker, GAutomatch, these were either manual, blob, or template picking. And then Topaz and everything beneath Topaz are using the neural network, the newer ways of doing things. Okay? And again, you can train each one of these programs with your data so that it goes through and it properly picks your specimen, or you can pick a model that comes with it, tinker around with the parameters, pick enough particles, clean up those particles, feed it back into it, okay, and improve your picking. And there are many outstanding publications that say it only worked because we do this, okay? So if your things are not working out, it's something to keep in the back of your mind that maybe you did not pick particles well enough. And I've had projects like this where you see one view is always being picked and the other views are not. And then at the end, you're like, I can't generate a model because all I see is a single view. Okay. Now, having said that, I want to go back to the manual picking. The manual picking is, number one, it's difficult because is that a particle? Yes, no. Do I put it in? Yes, no. There's all this decision process going on. And then if you look at these micrographs long enough and you look away, all you see is that micrograph. Your eyes are going to be shot, right? So you don't want to sit there and stare at this for too long because you might have nightmares about this like I did when I first started out. No, seriously, when I did my PhD in X-ray crystallography, and the first model building I did was you fit the model into an electron density that looks like a cage, and then I went home and I had nightmares I was in the cage and trying to get out. It's just, this is, if you do it enough, you'll start having nightmares. So having said that, so there's this problem, and there's also people like to go, oh, I like how that looks, I'm going to pick that, and you become biased, and you always keep picking the same view. You go, this looks the best, this must be pipe. No, it looks best because you like that view. So you introduce bias into the entire thing, and it's something to be aware of. Yes?
So, sorry, I don't mean to go back, but I'm interested in this neural networking using basically a given data set
Yeah.
to train to find your particles.
Yeah.
In your experience, how close does that given data set need to be to your particle?
So the data set's been trained on a bunch of different particles, right? So it doesn't need to be that close. However, having said that, I have also said that it doesn't work all the time, and it's better to train it. It's best to train it with your particles, right? But if you're doing it for the very first time, and you've never imaged that specimen before, you can either pick manually or you can pick using the generic way.
Do you artifacts, or do you train it on reconstructions, or
You train it on the particles that have been selected.
like the extracted?
Yeah, yeah, yes.
So with that said, what's kind of like your magic number for manually picking articles to put into one of these like training? Like is it like 1,000, 10,000?
Yeah, so magic number is the same as always. As many until you get sick and tired of it. Putting in the bias, it's something I say you can do, but it's something I've never done. It's never done. Because, you pick some and then I've gone through 100 micrograph. And I'm like, these are the best particles you can possibly ever pick. You do 2D classification, it's the same damn thing back out again. You're like, what the hell? I spent 4 days picking these things, right? My eyes are going, I'm running into walls because I can't see things in front of me. What the hell? So it's how desperate are you? How much are you willing to put into it? And how young are you? I'm not as young as I used to be, right? So my threshold for saying, F it, I apologize for my French, but my threshold for doing that is a lot lower than me yelling at my graduate student, did you have to do this if you want to get this stuff done? So that's what it comes down to. And I don't have a number for you. I'm sure there's people out there who would have some sort of a number for you. Right? Yes?
Some people in my lab, including myself, we were processing something up, and we noticed that, and this could be something else, but we were noticing that as our because we were retraining good 2D classes, the better 2D classes got, the less particles it was picking, but overall good particles. So like the first data set, we had 56 good particles, put those in, and then we retrained it, and then at the end got like 30,000 good particles. So we started with more good particles, and then when we gave it a better class, we picked less.
Did the classes you give it, did they have preferred orientations?
Maybe. We try to give it a good range. It was whatever particles looked the best. And I think we had a few orientations.
Okay. So one problem that you have, and I'll talk about this, is that the 2D classification that you do to put in the good class averages will throw out rare views. And at the end of it, it'll give you a biased, not a bias, but it'll tell you what orientations are most observed in your data, right? So you may have been, I'm not saying accusing, if you were feeding it a preferred orientation, then it's going to say, I'm going to pick the preferred orientation. That doesn't fit my orientation, right? So it does depend on what you decide, what you train on. So I'll talk about how you deal with the situation or how that's been dealt with in a situation like this.
It's a stringency thing too, right? So like if you tell at least crowds like look for this particle and it doesn't the extracted or the particles in the micrograph don't look exactly like that because it doesn't. I don't even know if it has to do with a lot. Or I think it has to do with more than just like a orientation. It can do with the defocus or focus or when you were imaging if it focused on like some other artifact in the micrograph that it didn't look like your particle, but it could be. I think there's a step where you can go too far.
Yeah.
So that might also happen.
Okay, other questions? Yes.
I got a question about starting with the provided model.
Yes.
What do you mean by that? Like an old model? Or is that completely biased?
Wait, where does it say that? Okay. Yeah, the way at the bottom. The little camera thing is blocking that. So you can have a model, let's say you're studying something where with a ligand bound to it, and you have a structure without the ligand bound to it. You can start with something like that, right? Another thing you can do, and we're jumping ahead a little bit with where your initial particle comes from, is you can do what you just did, AlphaFold. But generally AlphaFold, now there's multi-chain AlphaFold. How accurate is that? I don't know. How big can it get? Can it get up to 300 kilodalton? Can it get to the size that we're interested in with EM? So you can try something like that. You can get a model coming in from SACS. You can get a model coming in from SANS and try generating templates and picking using template picking or something like that. Okay, so questions?
I'm done not full with 60 well.
And
It looked fine.
was it correct, or you don't know yet?
I don't know yet, but it looked like how I would expect it to look like.
Okay. Okay.
But I don't know if it was like 100%.
Well, no, I would, yeah, I hope it's not 100% correct.
Yeah.
What the hell are we doing here?
But yeah, that's a good idea to use it as a.
Yeah, you can just be creative with it. So, okay. So, any other questions? Okay, so here you've got your CTF values, you've got your number of particles picked, and then CryoSpark, this is a curation window, does a bunch of additional things, right? With your CTF, you get a defocus value. What you also get is how good does the data fit with a theoretical CTF function, right? Is it a high correlation coefficient, low correlation coefficient? How far does the CTF, how do the two agree? And you could use all of these metrics to filter your micrographs down to the ones that you want, right? You can say, you can look at all the micrographs and say, okay, I don't want anything with a defocus range that's more negative than 2.5 microns, right? I don't want anything that's like 200 nanometers or smaller than that, or bigger than that, because we're all in the negatives. So you can say, okay, I want this window, everything outside of that one value, throw away. And then you go, okay, what else? And then you look at all your micrographs, you say, it looks like I have about 400 particles per micrograph. So if all the values look good, but I see 800 particles in this one micrograph, some funny business is going on, right? What could it be? Well, it could be that maybe that image comes from a carbon background, so more particles stuck to it. And you can say, okay, that's probably not going to give me as much signal, so I'm going to throw that away too. So you can use your particle count as a metric. Then you can say, okay, how well does the CTF fit? It has a good number of particles, it has a good number of good defocus, it fits in my defocus range, but the fit goes to only 7 angstroms. I don't want that. I want to go to 5 angstroms. I generally go to 5 angstroms, right? And then these tend to be few micrographs, but you could use a variety of, and you can use ice thickness as another one. Just it gives you a lot of metrics to say, okay, I want to use these values to extract particles only from these particular micrographs. Yes?
There's one that's like motion. You can like move it out.
Yeah.
Have you used that one?
So I don't use that one, but because I take the motion corrected stuff straight into here, right? And I don't do CryoSpark's motion correction. Because I don't do it, I don't get that output. But you can use that as well. You can say particles that move too much, or a micrograph that shows a lot of movement, throw that out as well. My guess is that if you have a micrograph that moves a lot, your CTF, you're probably going to have bad alignment, and your CTF is not going to go very high, right? So the CTF is already probably addressing that. And there's so much data processing going on that later on you probably just pull those out anyways. Okay? But there's probably additional things that I'm not talking about here. Yes?
So just like this example, it seems like you said a really nice defocus list for the data collection.
Yeah.
Which is either narrow range defocus values. Is that for a particular reason, or is that just for demonstration purposes?
Where is the defocus range?
Oh, sorry, just the average defocus. You just have a very nice distribution of defocus values, but
Yeah.
just use that central slice. Is that just for demonstration, or?
This is CryoSparks, I pulled it down. This is Harris's project, and it's what Harris chose. It's not what I chose. You're gonna have to ask Harris. I choose anything from 0.5 to 2 microns, right? 2.5 sometimes. Thinking back about it a little bit more, I'm going to change that defocus range, and I think I'll focus on collecting anything from 0.5 to 1.75, something like that. Why? Because you'll get to a higher resolution, because you don't have this I think Fred probably talked about it. I know he talked about it in his 2022 lecture, in that you get this, your high resolution terms go out further as your defocus value gets larger, right? So you need a larger box, and the CTF fit isn't as good as if your defocus range is lower. So there's many papers that have come out on this. I just haven't collected like that. Also, like I said, I collect a lot of tilts, so I can't go too close to the focus, because at some point I'm going to be over focused, and at the other time I'm going to be under focused. You don't always get the value that you're aiming for. There's some error in there. Questions? Yeah.
How important is this curation stage? Because I guess particles that are like on carbon
Yeah.
or like with bad motion, they're going to get removed like
Yeah.
classification. So how important is it that you get rid of bad micrographs?
That's a very good question. The answer is I don't know. I like deleting things. So I go delete, delete, delete. It's not scientific, it's just one of my things.
Yeah, I guess my comment was going to be like all of my processing previous to this was in Reliant.
Yeah.
You never curate
Yeah.
micrographs in Reliant.
Yeah.
You just take them all through.
Yeah,
But in CryoSpark, yeah, you can be really like selective about it.
yeah, yeah.
It seems to me like it doesn't make much difference.
It may not make much of a difference. Because you know, when I do all my filtering and then I look at what wasn't picked, I mean, these are like really bad micrographs, right? And it's like, there's no way a particle on that micrograph can survive the entire thing, right? It's already been beaten up to a pulp. How is it going to survive the entire process? So I think at the end of the day, you probably are correct. It's just I've never looked at that.
I can see that use too, where it's like, I had a data set collect where there's a power outage, like 2/3 of the way through the collection,
Yeah,
and the beam shifted to bottom right corner.
Yeah.
And if you look at that curation step, it's
Yeah.
like, oh, everything's, average deep focus,
Yeah.
and it just like suddenly plummets.
Yeah.
For the last 3,000 images. And
Yeah.
you know that's virtually useless imaging.
Yeah.
It's just like
Yeah.
black background with a tiny little white dot in the corner.
but one thing that one reason why I do it is if you have a significant number of micrographs, template picking will always give you an answer, right? If you have a black image, it'll give you a whole bunch of things, and you got to process all that, right? If it's a significant amount, then your time is being wasted on processing these things. So that's one of the reasons why I do this. How much do I save? I don't know. Yes.
In my lab, we also use the CTF threshold.
Yeah.
I always wonder why that is a magic number. And if we have like an ideally really big data set,
Yeah.
we go even lower.
Yeah. So there was a paper quite some time ago where they started looking at this. And they saw that if you include data worse than a certain resolution, then you're not going to get to the high resolution term, right? So they went through, this was from NRAM with Bridget Carragher and Clint back when they were at Scripps. And they had this ginormous data set, and they went systematically through all of these things. And they saw that, yeah, if you cut it off at this point, then you're going to get to higher resolution terms. Now, some people might say, take that 5, move it over to 4, right? But then you have to collect a lot more data because there's always error involved. And what is your ultimate goal? Do you want to get better than 1 angstrom? I mean, I know the microscope can get there, but is there a story at better than 1? Particularly to apophoric ferritin. Does it matter how much those hydrogen bonds are being stretched? In an enzyme, absolutely yes. But with a lot of the proteins that they're just involved in binding other proteins and stuff like that, that hydrogen bond is not so significant. At least we can't make much chemical sense out of it. So there's a lot of give and takes. What's the story? Yeah.
Also, you can also kind of, like you showed it the scatter plot in the upper left, but you can
Yeah.
also view that as like a histogram.
Yeah.
And you can select like it's basically Gaussian, right?
Yeah.
You can select
Yeah.
the set with the most 16% of particles or whatever.
Yeah.
Those are the best data you have, and typically it's around like 3.
Yeah. There's many ways of looking at it. Yeah.
So I'm just thinking of what you said about this curation step in Reliant.
Yeah.
I think there's also this subselect part in Reliant that works almost like this as well. Yeah, so I think we use that in the lab, and you can just use that to create your data set after CTF refinement. So you just remove all the data.
But you manually remove it, right?
Yeah, no, not manually. There's this select function.
Oh, yeah.
So it works similarly to this version.
Yeah, the sub-select, it's another job.
Yeah.
Right, yeah, I don't like. Well, no, so I come from so I'm old, number one. So GUIs were like, there weren't that many GUIs when I was doing my graduate studies, and my advisor was like, one of the things he told me is that you need to look at the code of CNS and understand what's happening. I'm like, what? I never did. But that was, and I wish I had, because I look at things more closely now. But the point is that I like to use the command line, and I like to write scripts, and I like to have things automated, and I know what's going on. So with Relion, when you do all of these job submissions, number one, it creates way too much stuff, and so number two is you lose control of what's going on. So yeah, so it probably has a lot more functionalities that I don't use because I just write a script to do what it's already doing. So it doesn't create job number 245. I'm still in like job number 5. Okay? All right, but doing all of this, you can do things manually as well. All right, so that's the curation part of CryoSpark. So particle extraction. How big of a box should you use? I've seen publications where the box is really tight around the particle. It's not a good idea. So back from a long time ago, I was taught to pick a box that's 3 times bigger than the size of your particles. That's just a general rule. Why was that the general rule? Well, because when I was, from a long time ago, it was said to use defocus values around, don't go less than 1, don't go close, pick something from 1.5 to like 3 or maybe 3.5, right? And that's just because the algorithm for alignments weren't that good. So they needed more contrast. Again, this was quite some time ago. So that's why the box was so big. Now, I think Fred talked about this, because I know he did in his 2022 lecture, that the signal gets delocalized according to the energy of the electron and to the defocus value. The energy of the electron you can't touch, that's what it is. But the defocus value you can change. So if you make it more defocused, then you're going to have more delocalization. Your box has to be bigger, right? And you can calculate what your box size should be using this equation shown up here. R equals delta times lambda times F. Everything is described on there. So you can say, if I want a 3 angstrom structure, that's what F is, the desired resolution, and I have a particle that's 100 angstroms in size, how big, and I want to use defocus size of 3, how big should my box be? And you can use this to select the proper size box. If your box is too close, too small, you lose your high resolution terms, your alignments are not as good. If your box is huge, nothing's ever going to get done because you're going to run out of memory, right? So, or it's going to be extremely slow. So you got to pick the right size box. Going through all of this, it seems that if you stick to that rule of thumb, 3 times bigger than your particle size, you're going to be fine, right? You don't have to worry about your defocus. This becomes problematic when your particles are huge, right? When your particles are huge, every pixel counts. I mean, I have particles right now that would fit nicely in a 1280 by 1280 box size. I can't process it, right? I need a large cluster with strong GPUs, with lots of memory to process the data. So then it becomes, oh, geez, I should have collected data closer to focus so I can have a smaller box size so I can process it at home. So these things actually do become important, okay? Particularly with large particles. Now, what is the size of the box that you want to choose? I've seen boxes that are just random in size, right? When someone starts out first, what's your box size? 50, why 50? It's nice, right? What happened is it's not nice. You're supposed to think about this. So if you want to think of it purely in a computational sense, and you want to think of how fast it runs, you want to pick an even number, with the exception of one program, PFT2, or what is it? PF2. It was James Conway's program that uses that uses odd box sizes. Everything has to be positive, right? And you want to pick something with a low prime factor, prime numbers being 2, 3, 5, and 7, so that the Fourier transform algorithms run a little bit faster, right? What's faster? It may be that if your box size is 200, it runs maybe like 5 minutes faster than if it was something of a different size, right? But this is particularly true because GPUs are so much faster. But this is just throwing it out that you do want to think about what your box size is. Okay, there's low minimum size to it, and think about the box size even number with a low prime factor as well. Okay, any questions? Okay, so yes.
Just when you get when you're choosing the box size, would you want the original box size to have those base numbers, or when you downsize it, you also want to make sure it still has those base numbers?
Both. So if you read like CryoSpark and Relion, they say this is not necessary, but it's not necessary, but it works faster, right? I downsample. To 64 by 64. Why 64 by 64? Because the algorithm, and I look at this naively, but the algorithm doesn't care whether you're working on a transmembrane protein, whether you're looking at an extracellular protein, whether you're looking at a cytoplasmic protein. It's aligning pixels to pixels. That's what it's doing. So there's a minimum number of pixels that it needs for it to align properly. Imagine if you go down to a single pixel, everything looks the same, right? So what's that magic number? I played around with this when I was a postdoc for some bit. It ended up being 64 by 64, right? So I always downsample to 64 by 64. Now, it could be that if you have a very small particle, that you can't really downsample because now you don't have enough pixels to align on, right? So I downsample to 64 by 64. It puts me at the box size that the algorithms like, and now it aligns a lot faster, right? And I do it solely for going faster. I'm not saying it gives you better resolution. You just go faster. It may be the wrong thing to do, right? But if you're working on something that's bigger than 250 kilodalton, my recommendation is downsize, right? If you're working on something that's 40 kilodaltons, probably not, unless you go to a really high mag and you still have a lot of pixels to align on. Yes?
So says you have a box size, a particle box size, you see a particle which is a neighboring particle fitting into that. How
Yeah.
does that affect the bigger spaces of reconstruction? Show up.
So essentially, if you have you have a group of particles that are hanging out. And the question is, if you pick one in the center, particle number 1 is in the center, particle number 2 is this guy, and particle number 3 is this guy, what the algorithm can do is it can align all of them, put the center in all of them. So essentially, if you have 1, 2, and 3, all these two, the alignment can pick this and align onto this one, right? So that way you have duplicate particles. And what's going to happen is that because you have duplicate particles, you're going to get, your FSC is going to tell you got to a higher resolution. Because particle A is going to be in the first half of the data set, particle A again is going to be in the second half of the data set. So you can, and because you know where you picked, the XY coordinates of where you picked, and you know how much the translation was, you can essentially, you can ask the program to get rid of duplicate particles, and it'll do that translation for you, and it'll say, okay, I've gotten rid of all duplicate particles. Right? And that's what it's looking at after you've done all the refinement. And then you can go forward with your refinement. Okay, but if you don't do that, you'll get really high resolution. And you look at the map and you go, oh, it doesn't look like it's a one-angstrom structure. Questions? Okay. So next is 2D classification. This is what's done traditionally. And I'll talk about an example where this is not what you want to do. Just a list of programs that you can use. Again, there's more than this. And the idea behind this is you want to remove the bad particles. What's bad? Bad is something like, that's bad. This is bad. This is bad. This is bad. Something that you can definitely tell that's bad, right? Or you can see the edge of carbon, or you see all these junks. But if it's not any of those, like, is this a bad particle? Doesn't look as good, but is it bad? Right? So it becomes a little tricky. My suggestion is that if you do go this route to not get rid of particles that you can't definitively answer as bad. Okay, this is particularly if you're starting with something you've never looked at before. If you know that I've looked at this before, I know it's not supposed to look like that because I calculate projections and there's no projection that looks like that, so I'll throw that out. If you don't know that, keep it. Right? You can. There's additional steps you can throw out. So, and the idea is you compare all the particles against one another to separate heterogeneity. What's heterogeneity? In the simplest context is particle orientation. One that's laying on its side, the other one's on its head, the other one on its other side, on its back. So they're all going to look different, and you can use this to pick out different orientations, or you may actually be able to pick out configurational differences. What's an example of a configurational difference? Ribosome. You can pick out 70S from 50S and 30S. And you can say, I don't want to look at 30S. I don't want to look at 50S. I want to concentrate on 70. Right? But then there's particular orientations where you can't differentiate between 50 and 70. Right? So the idea is to clean up the data. However, what's clean is what you see a lot of, meaning rare views are going to be thrown out. Okay, because you can't get a good class average. Questions? Yes?
So I've gotten different advice from people about how many classes to do.
Yeah.
So they go from like 100 to 300 left. What would you say was that? You should see.
Skipped it. That's what this is. Right? So everyone's got a different way of doing it. That's why you get a different answer. And every project's going to be different. The way I do it is generally what you anticipate is to see 100 to 400 particles per class. Right? You got to start from somewhere. I start off with that. Then you say, then my experience has been if you ask for too many classes, and I say too many because at the end of it, everything collapses into a single class. The algorithm goes, everything goes into the same class. Right? So what do you pick? So I say, I like the number 64. I just like the number, and I'm superstitious. So CryoSpark's default number is 50. I go, 50 is close to 64. I'll stick to 50. Right? But if I have 2.5 million particles, I don't want to put 2.5 million particles into 50 classes. There's no way you can properly pull out junk and proper orientations. So what I do is I got 50 classes. I have 2.5 million particles. How do I deal with this? 2.5 million particles is going to take some time to process on one GPU. So I think I'm smart, and I take that and I break it into 100,000 particle bins. And that's what all those things are up here. Each one of these is a 2D classification on 100,000 particles. Now I can submit that to GPU number 1, GPU number 2, GPU number 3, GPU number 4, and I just load it up. And in 2 hours, it's all done. Yes?
How do you do that? How do you take the 2.5 million particles that because usually you just drag and drop, right?
Yeah, so there's a job that breaks it into subsets. And you just say, randomly break it into 100,000 particles. And it says, okay, and then it just breaks it off into that much. And then each one you process separately. Yes?
I mean, so this is specific to CryoSpark, but with 2D classification, you can use multiple GPUs, right?
Yes.
Does that not scale as well as just for the
The overhead associated with using multiple GPUs has never, ever, in any program I've ever used, been equivalent to breaking the data in multiple sets. I've never seen 100% efficiency. I've seen close to 80. This is no matter whether it's in crystallography, whether you're doing this protein engineering design. If you give each GPU its own job, molecular dynamics, if you give each GPU its own job, it'll run n-fold faster. Because it doesn't care what the other one's doing, right? Your I/O is going to become problematic, right? So that's going to slow it down. But that I/O is going to be there no matter what you do. You can only reduce it if you pass it to different systems. So in my experience, breaking it down, and you can do this with raw ion too. I used to do it with Reliant. You just use split-L, you give it the number, and it'll split your star files into a whole bunch of, but you have to make sure you have to write a script that puts in the header, right? So then now you have a whole bunch of star files. you have you write a script that says submit all of these. Submit a fourth of all of these scripts to GPU number 1, the other fourth to GPU number 2, GPU number 3, GPU number 4, and each time one finishes, it goes to the next one. And that's parallelized. Right? CryoSpark makes it a little easier. And then I don't have to worry about teaching someone how to write scripts, processing data, mental overload, all these problems that's not associated with science. Okay? Any questions? Very good question, though. Okay. So what I do with CryoSpark is now I have a whole bunch of 2D class averages being run. They finish, I go through, I pick my good particles, my bad particles. Because that's all you can do. Good particles, bad particles, good particles, bad particles. And then I take all my bad particles, and if I have, and generally what I do is I combine them until they reach 100, right? So I might combine 2 of these, like I do here, and that reaches 100,000. I do that with the good and the bad. And then I take each one of those and I process again. So I only process in 100,000 chunks. This is purely for speed, right? I submit it to multiple GPUs, and rather than taking 2 days, it takes like 5 or 6 hours, okay? And then what I do is I take all my bad particles, I put them together, and for sanity check, I run another 2D classification to see, is there what was rare in the 100,000 that you got rid of doing 2D classification may now be enriched in the junk particles. And you may pull it out. You may pull it out. And I say may because you may not. So, any questions? All right, so now I have a whole bunch of good particles and a whole bunch of bad particles. I've checked the bad particles are bad. I look at the good particles, I say enough orientations, I say, okay, I don't want to deal with the bad particles anymore, I gotta go forward, right? But you can play with it until you're sick and tired of it. I just got tired of it a little faster. Okay, so no questions. So, values to play around with. Number 1, don't ask for too many classes. Don't give it too many particles. Things you can play around is the radius of search. CryoSpark allows this. CryoSpark gives you a whole bunch of things that I've written up here. The turn-off force max over post shifts, the initial uncertainty factor. All of these values play around with. I would say the values that I've seen have the most effect are the radius of search, the online EM iterations, 25, which is what CryoSpark suggests, sometimes is not enough, and you need to go 40, right? The set batch size per class, this is how many particles it uses initially, so I would also change that as well, okay? With Relion, I play around with, again, with radius of search. You can write a script that just changes the radius. It starts from a large radius and progressively gets smaller, and look at your class averages and see, are you seeing additional orientations? This particularly becomes important when you have crowded particles, right? And you don't want to have too many of the full particles of the neighboring particles. And then the other value with Relion is your tau fudge factor. This was something Fred talked about near the end. And it's the number that puts more emphasis on your experimental data. Okay? Questions? Yes?
What's the force max on the coaches?
Oh, geez, I forget which this one is. It's in my notes somewhere. I thought I'd remember. Apologies, I forgot. Okay. All right, no other questions. Okay, so 2D classification. Then your initial model. Initial model historically used to come from random conical tilt. Anybody knows what RCT is? Yeah, see, that's the problem. We all forget. RCT is you generally, I've never seen it done in cryo. It was done in stain. You take a picture of an untilted specimen, then you tilt it with a known angle. You take a picture of the same thing, and then you classify all the untilted particles, and then because you know what the tilt is, you know the angle for the other orientation, you can put them back together and get a general model. That's random conical tilt. There's orthogonal conical tilt, which is you tilt it this way and then you tilt it this way, and you know the two tilts, so now you're seeing additional view. It's just a play on random conical tilt. Orthogonal conical tilt has its own problem because the overlap between the two is much smaller. So it never, I think because of that, it didn't gain as much use. Then there's common lines, which is the Fourier transform of your image is a slice to the Fourier transform of another image, meaning two different orientations. If you take the Fourier transform of both, they will share a common line with one another. And that common line defines your orientation. This used to be a method that didn't work out so well, but then when you couple it with class generating nice class averages, it works extremely well. So I used to use this a lot when I was doing negative stain work, but nobody does that anymore. And then there's also tomography with subtomogram averaging. This is something that you generally do when you become desperate, because subtomogram averaging itself is quite hard, right? The software isn't streamlined. It's not as obvious. It's not as for lack of better word, it's not as dummy-proof as single particle analysis. It's not as mature. The way CryoSpark and Simple and Reliant do it, and this all started with Simple, is that you assign a subset of particles are selected. They're assigned random initial parameters. And then the reconstruction and then stochastic gradient descent is used. This is what Fred talked about to get you to a model that looks much better. So this started with Simple, and then CryoSpark and Reliant used variants of this to make their initial models. Okay, so it's not common lines, it just starts from random. And this works remarkably well. Okay, so it's the go-to for everything, unless you have preferred orientations. If you have preferred orientations, it's not going to work. And that's the next slide. That's the next slide, yeah. So, okay, and then now everybody wants to stay in the microscope world. I like stepping out of it, right? Other ways you can use small angle X-ray scattering, small angle neutron scattering. I've seen these models. I don't like SACS because it's too low resolution. But I'm an idiot. Oh, I think I got disconnected. No. I may have gotten disconnected. I did get disconnected. Okay, so Zoom. Are other people still connected?
I got you.
Okay, so I'm coming back on. Anyway, so SACS envelopes work quite well. SANS envelope also work. I think the other image I had up there is you can use the AlphaFold models. You could use their other Robetta models. You can use, for example, if you have structures of the components and you have cross-linking more, share screen. Okay. Okay. Okay, so hybrid approach. So let's say you have structures of the components, but none of the full thing, and you have cross-linking data from mass spectroscopy that puts somewhat of a model together. You can actually use that as well, right? So you're not restricted to what most people talk about. You can get creative about it. All right, so that's your initial model. Questions? All right. I recommend generating multiple initial models. Why? Because you generate multiple models because the subset that it may have randomly selected may not have been a good model, good subset. You select it because if you ask for 8, 7 of those 8 are bad, 1 is good, you can use the bad ones to pull out bad particles. You can still using it for filtering. Other possibilities, you may actually have configurational differences, and I have an example of this. And configurational differences means the chemical composition is different, right? So you can use these multiple initial models to say that, oh, look, now let's do 3D classification using all of these, right? So I recommend generating many. How many? Until you're sick and tired of looking at it, right? Or your PI comes running in saying, stop, you're burning up all the hard drive, stop doing this. Starting size of what frequency you should use, this is something that's generally forgotten, is that the size of your particle, if you have a particle that's only 60 angstroms big, and you do a low-pass filter to 60 angstroms, all particles look the same. You have no features to align on. So that initial frequency, or the low-pass frequency, is something important to remember. My rule of thumb, take your particle size divided by 5, and use that as the lowest resolution to align on, right? That's what your low-pass filter. If ribosome, you can do 300 divided by 5, you get 60 angstroms. If you have a 200 angstrom particle, you divide that by, you low-pass filter to 60, you may not have as much features and it may not work out, okay? And there's also a frequency, the highest, lowest frequency used in the initial model that's also, and then you should put this value in. Also use C1 symmetry. Don't put any symmetry at this point. Yes?
Do you typically do the step on your entire data set or just a small subset?
That's a very good question. You could, I would do it in a small, I do it in a small data subset, and then you can say, I do 2 on each one. And do it until you see the same thing happening again and again. So you have, okay, so I would do, no. Okay, it automatically selects a small number out. So it's already doing some sort of a random selection. So even if you get something huge, I would do it on the entire thing. Do it on the entire clean stuff. Unless you're concerned about rare views, and I'll get to that. I'll go faster.
I found that you can be really slow, which is really good for protocols.
Yeah,
Eventually, you'll try to classify everything.
yeah.
So I heard not only for the production kit,
Yeah.
just the entire.
I give it the entire thing, but I give it the entire clean thing, but remember I do it at 64 by 64. Right, so that makes me have to worry about less. Question back there? Yeah.
2 questions. How do you use a bad initial model to remove bad particles?
Okay. So that's what you do 3D classification for. Right. You do 3D classification. Another question?
Second question is, you're using already known model.
Yeah.
For instance, just like you gave example, the structure with ligand and the structure with ligand. So you're using that as your initial model. How low should the low pass filter be?
1/5 the size of your particle.
Okay, so it doesn't necessarily affect, and the resolution of your node structure doesn't necessarily affect the low pass filter.
The resolution of your structure doesn't affect the low.
I mean, the initial model, now you have a known model that
Yeah.
maybe is 3 angstrom.
No, you're okay.
Putting that as your initial model.
Yes.
Then you want to low pass the filter.
Yes.
So how low should that be? Should that still correspond to your particle size?
Yes.
Or to the initial model?
To your particle size. Why? Because this is the ratio that I say that you start seeing features that are useful. Right? If you're too aggressive with it, it looks like a football, it looks like a basketball. How do you align to a basketball? If you're not aggressive, if you don't low pass filter, then you have model bias. That's another worry about. So okay. So the next thing is you do 3D classification to get rid of bad particles, right? You can pull out conformational differences as well. One thing that's, I guess, not talked about is you can pull out preferred orientation. When you go through these manuscripts and they go, we use 3D classification to get rid of the bad particles, and we had a bunch of reconstructions that were at low resolution. Well, if you look at those reconstructions, if they rotated, you'll see that they're elongated. And it's elongated because it's preferred orientation. So they're pulling out preferred orientation out of it. It's not that they're bad particles, right? So you could use it to pull out preferred orientation as well. There's a problem with this, is that you could be pulling out good particles can go into a garbage thing. So you got to be a little bit worried about this, right? And if you get to a high enough resolution, who cares? You got your story. Question, yeah?
Does this clarify conformational heterogeneity?
Not good enough. Not good enough. Whatever conformational heterogeneity you see, I would say you got to do more. You gotta do more. So here's 3D classification. This is by Oliver Clark. Francesca Valisi did this, and they're looking at ankyrin. They generated multiple ab initio models, and right off the bat, they saw that there's heterogeneity, and they refined all of these using cryospark and fed some garbage stuff into it to pull out bad particles as well. So the initial model told them right off the bat that you've got configurational heterogeneity. And with that knowledge, you can move on forward and know exactly what you need to do and know what to look out for. So multiple MAB initial models, and then there's local refinement. There's all of these things that I probably don't have time to get to. Let me go through this, and you can ask more questions during lunchtime. In the events that you have rare views, you do 2D classification, top right, you see nice things, but as you notice that you don't see any end on view, right? It's just being thrown out. You don't see it because it's being thrown out. So 2D classification immediately doesn't work. And this happens in Eva Nogales' lab. This ended up being a big problem with a lot of things that they worked on. So what they did was they extracted the particle, immediately went into 3D classification, throw out the bad particles, enriched for the rare views, and they've concentrated on those rare views. Okay, so you can do that with Reliant by playing around with the tau fudge factor. And here they picked a particular class that they say went to a high enough resolution. Then you do focused classification where you don't do any alignment. And then you play around with the tau fudge factor using various numbers shown here. This is empirically determined. And you see which one gives you the highest resolution that you can get. That makes sense. And you go forward with that for your publication. As you can see here at the angular distribution, you see blue everywhere. You see a lot of red, which there is preferred orientation, but you are seeing additional orientations that you would lose if you processed in 2D classification and then threw out the particles that don't give you good class averages. So do the 2D classification. If you see preferred orientation, go, geez, I hope there's rare views that I can use, and then go back and do the 3D. Okay? And then the next thing you can do, there's signal subtraction, focused classification, playing around with this tau fudge factor. This is with the spliceosome, where you have a 2.8 angstrom core structure that's very good, and everything around it is blurry, doesn't align well, and you can use this focused classification without alignment and signal subtraction to pull out the high resolution structure for each component. Okay?
Reza, this is Fred. I skipped over the tau fudge factor too quickly. In the Reliant iteration, the Wiener constant is sigma over t, and t is that fudge factor. So the bigger you make it, the smaller that Wiener constant is. That is the less regularization.
Yeah. And more emphasis on the experimental data.
Exactly.
Yeah. Thank you so much. So, and then signal subtraction. How much time do I have? I'm done, right? With time. I'm basically done. Okay, so last 3 slides, just quickly. There's signal subtraction, there's multi-body refinement, cryo drag industing, and then there's flexible refinement that cryospark does. These are the last 2 are the two most recent things going on to show continuous conformational heterogeneity, right? Stepping away from discontinuous movement to continuous movement, trying to get, and there is danger to be had in here, so just be careful with what you see. But it's something very cool. Okay? I guess I'm out of time. I'm also out of slides, so I guess I'll answer any questions during lunch. Yeah.
Real quick question. The 3D flexible refinement that you had, is this okay, I see it now. The prospect. Okay.
Yeah.
Okay.
Okay.
So we're going to break 15 minutes, Fred, so the students can grab lunch, and then we'll have a roundtable while the students eat, basically from 1 to 1:30. I believe that's what the schedule is. Okay, so Reza, grab food first, just so you can have it, and then the students will follow shortly, and we'll be back quite soon. Okay. So the only way a roundtable will really work is So Reza has the lapel mic, and then I have the handheld, but we're going to pass it around. So you have a question, please make sure you use the mic. And the idea, it's free-form questions. Fred, can you see the room? We set up the camera again.
Yes, very nice.
Okay, great. So then I'll just kick it off with a general question. So how poorly would it be to always collect overfocus? So if we were to collect an overfocused data set versus a defocused data set, assuming we can do perfect CTF correction, would there be a preference?
It'll just be harder to see the particles, pick them. But otherwise it should work. I remember...
Do you know if the modern programs handle the CTF correction well? When you collect a little bit of overfocus and defocus, when you sort out particles, are we primarily also throwing away a lot of overfocus images?
I know it, overfocus and underfocus are really hard to tell apart from their phone rings. So I bet they have problems with that. Hongwei Wang published a paper. They have a Krios with CS corrector. And of course, with the CS correction, then the CTF is almost identical over and under focus, and they show that over focus worked fine.
Opening the floor up for questions. Anything you want to ask. But make sure you use the mic. Otherwise, I'm going to start calling on people. Okay, Curtis.
I was wondering what you thought about the 3D classification algorithms, both CryoSpark and Reliant, and how they compare, and whether one software does better than the other.
So I use 3D classification as it's traditionally done, simply for cleaning up particles. And then I get into focused classification for teasing out the differences. By the time I get to that, I used to go with FreeAlign. However, I've seen Reliant's algorithm actually do comparable to what FreeAlign used to do. So now I don't have to do a second conversion from Reliant into FreeAlign. So for CryoSpark, if I see conformational differences or configurational differences, I don't separate the data yet. I'll separate it later on. However, I have had a lot of good results coming out if I do 3D variance classification.
Okay.
Right, so these 3D variance is a little bit more like focused classification without a mask.
Okay. So in CryoSpark, one of my concerns was with heterogeneous refinement. It seems like, so you have to give it some starting references, but it just seems like if you give it a starting reference, you'll get back the same starting reference.
Yeah.
And if there's some very minor population in your data set, it just won't be able to pull that out. Do you have any advice for trying to identify these smaller populations in CryoSpark?
The smaller populations are what? Particles or are they junk?
Particles. So like
Particles.
actual, maybe some rare conformational states like an enzyme or something.
Oh, so I think CryoSpark now has focused classification. I have not played around with that. So I would go towards looking at focused classification to see if you can pull out those small differences.
Okay.
Do you need a mask to do multi-body refinement?
Yeah, you need a mask that defines each body.
Okay. And that mask, you just make it in Chimera?
Yeah, Chimera is a fantastic tool for that.
And is it like, so I've seen like the tutorials where you just make like a giant circle.
Yeah.
And then you just flatten out like a certain area.
Yeah,
and that's
yeah.
usually acceptable?
So, yeah, but
Go
what I would go to Segger. I used to manually use the erase tool to manually delete what I don't want, because that was fun. And then I had one of my people was like, oh, I want to try Segger, and they used Segger, and it did an extremely good job. Okay. It was a bit depressing, but that's that's what it is. So yeah, Segger does a fantastic job.
Okay.
Yeah.
In Chimera, how do you make the mask soft?
You don't make it soft. You make a mask, and then I take that into Relion, and then I make it
Gotcha.
soft. I do the erosion. Yeah.
CryoSpark has options for softening your masks as well. Would
Yeah.
you import it? Yeah, yeah.
Yeah. Yeah. I use Chimera just like it's a 3D painting tool. That's how I use it.
So I have a question about, so you talked about the EM algorithm. So Relion is now also using the VBAM algorithm. What do you know, like kind of what the difference is, and why there would be an advantage over like using that over using the EM algorithm, or is there an advantage at all?
I don't know what it is yet. I've got to read the paper.
Okay.
So I see that in CryoSpark you have three options of 3D classification. One is simple input. Another one is, I think, SCA, and there's third option which is simple. Simple input and SCA, the three options there. So do you play with those options, or do they make a difference? I mean, which one?
In CryoSpark?
Yeah.
Is that part of the new version, or is this an old one?
It has been changing continuously, so really I can't refer to which version.
Yeah, I haven't played around with the new version too much.
Okay.
Yeah, I haven't had that much time to do a lot of data processing lately.
It's changing a lot, so really it's hard to keep track with that, what they're
Yeah,
introducing.
yeah.
Still don't know how do you do focus classification in CryoSpark. I know you can do focus refinement.
Yeah.
But classification, like, do they have options for that?
Again, this is something that I haven't tried, but I would imagine it's like everything else. You give it a mask, you've got your map, and then it looks for differences in that masked area rather than the entire thing. So you identify differences looking at a smaller area rather than the entire thing, right? And then what you have to be careful with is that it can't be too small. Like you can't tell the difference between an alanine and aspartic acid. It's too small. It has to be a particular size where where it's large enough for the signal to be significant enough. Like a domain would be something like maybe I think 12 point. I've tried things with 12.5 kilodaltons. It was too small. Didn't work. So Relion has this new blush algorithm that works on things that are much smaller. And Shores was talking about a 40 kilodalton DNA binding protein. So it might work with this. I don't know if you can do focus classification with this, or it's going to get smaller at some point, but there is a limitation at this point.
That blush algorithm, that's full, that's not like
That's a full thing.
It's not, the whole
Yeah.
process is through the whatever the blush algorithm
Yeah,
is.
yeah,
I want to visit that. Like, in the shop.
yeah, yeah.
Oh, related? Okay.
Yeah. Like, how do you know the mass is too small or that you don't have any heterogeneity there? Like, how can you tell?
Well, so you run it and it doesn't work, right? And you go, I hope I'm good enough that nobody else can get it to work either. And then you run around and you tell everybody it was too small. The reality of it is that you might give it to your buddy and they make it work in 10 minutes and you're like, oh, geez, right? So I haven't seen any papers where they got a 12.5 kilodalton protein to work. So that's why I'm saying it's too small. But I may be completely wrong. It may not be too small. It may not be.
I guess it matters a lot whether you're doing alignment or not, right? Is there a way to turn off alignment in CryoSpark?
The 3D classification in CryoSpark is by default without alignment. It takes the original alignment from homogeneous refinement.
Oh, okay, super.
Okay, I was wondering if there's, I know in Relion there's movie polishing. So in CryoSpark, is there anything that corresponds to that in CryoSpark?
Yeah, I think so, yeah.
Okay, what would that be?
I don't know, because I was going to Relion and runs Relion's algorithm. I think, no, do you have it?
Yes, isn't it the reference-based motion correction?
Oh, the reference-based motion correction. Yeah, I
It's
mean,
like
yeah.
their version of polishing.
Yeah.
But we were just discussing, like, you prefer to use Reliant.
Yeah,
and
yeah.
People, I guess, I'm not sure if they're comparable.
What's corresponding, maybe the same thing that can run movie polishing in CrowdSpark, just like that.
That's the reference-based motion correction. Yes. It's the same thing. It's like a per particle polishing.
I do have a general question for everyone here, and the experts as well. But like, something I haven't been able to get like a good answer on, or at least what I think is a good answer. Micelle subtraction from like your reconstruction, or is like what's everyone's best way that they've found to remove your micelle? Is it just reduce like the threshold in Chimera? I noticed that like, is there a method to kind of remove density from your map in Chimera or another, maybe something like that, based on the resolution that's imparted by like CrowdSpark's local resolution estimation? Does anybody have any strategies for that? That's like, any strategies at all?
You can do a signal subtraction with a mask on the mycel, and then get alignments and apply those alignments to the original particles without signal subtraction. And so you'll be aligning on the protein.
Okay.
My answer has always been to do it in Reliant. And when you do post-processing, just use a mask, which you still have all your protein, but you've masked out all the
So you make the mask in Chimera.
In Chimera, yeah, you just play with the threshold, so it's at a point where you don't see the micelle anymore, but you haven't clipped out your protein.
Okay.
Fred, maybe you can also, on the similar lines, not just micelles, you've been working on ion channels and liposomes, and how do you handle that, and how do you subtract the lipids? Memory.
We assume that we ignore the protein and just fit the liposome and subtract the membrane model from everything. It's not perfect. For the final steps, like polishing, we go back to the particles with membranes.
So to pick on you, Fred, so something we didn't really cover in this class yet is FSC, but perhaps you can comment on angular sampling and why the core we resolve very well and periphery we don't. And then you've actually made tools to give some indication of local resolution.
Yeah, so FSC works entirely in the Fourier domain, and so you're operating on absolutely the whole volume, including all the empty space around it. So that's tricky. You can make the resolution appear better by masking away a lot of the excess. I'm sorry. I turned down the echo. By masking away the empty volume, that helps a lot. So the problem is, of course, if you have predominant preferred orientation, you're going to get lots of resolution and really good resolution from that, and not in the other direction. So one tool by my colleague Hemat Tagari and people from Sorzano in Spain is you don't do FSC over the entire sphere. You do it in a cone. You do selected areas around the sphere, and you have a separate FSC at each position. And then you can sort of give a histogram or just show a band of where the FSC is worst and where it's best. I think that's a very useful tool.
So then I'll pick on you, Reza. How do you use FSC or not? Because at some point in time, you talk about classification, sorting. So ideally, yes, you have enough contextual information to understand the biology, but when are you using resolution as a criteria? When are you using other factors as a criteria?
So I'm not, I look at the density. And you can have again, I like to go to extremes. You can have a 1.5 angstrom data set. And if you can't see the side chain of the amino acid that is in the active site and that you're particularly interested in, what does the resolution matter if you can't see it? So I go with what I see. And if the referee has a problem with that, I show the density. And rather than saying, oh, but it's at 2.5, it's at this number, and there's no density that means anything at all. So I don't use the FSC other than for reporting it and having the referee be satisfied with how the FSC looks like. I do use local resolution. Again, that's just for the referee. I think I need to see the density. And you can always have beautiful density that somebody modeled into incorrectly. And what does resolution mean in that regard? It doesn't mean anything. So there's additional metrics that people, and I think, I forget what the name of the individual's name is. I think it's Daiske. He's at University of Purdue. And he's done all this beautiful work where he's gone through a lot of these EM structures and he's compared them to the density. And he said that a lot of the earlier on structures that were deposited were just, the models are just bad, right? And this has nothing to do with resolution, and it has to do everything with the individual who did the modeling. Now, I don't want to criticize anyone, because modeling at 3.5 angstrom resolution is very difficult. And you can only do it if you're highly experienced, and the people who are doing it were not experienced, so I'm not criticizing them. But this is the point, is that resolution doesn't mean anything if everything underneath it hasn't been built in properly, and it's not being interpreted properly as well.
So on the topic of interpretation, now that we're understanding more about biology, sometimes we see bordered water or ions. So then how are you sure that what you see, well, you might not be able to differentiate between is it a calcium or a water, but how do you know that it's actually something?
Oh, so what I would do is I would look at the coordination number. If it's any sort of a metal, whether it's a rare earth metal or a transitional metal, there is tons of data out there in the inorganic world that says, okay, if it's a calcium, it's octahedral geometry. If it's this, it's that. The distances between the waters and a potassium is this much. The distance between the calcium is this much. And if you say it's a calcium, but you look at the literature and everything is telling you, no, it's not a calcium, it's a sodium, then I don't care what your resolution is, because you're essentially saying, oh, there's 50 years of data that's completely wrong, and my structure fixes 50 years of data. Well, that's a tall hill to climb, and you got to have a lot more data than just one map that goes to a really high resolution. I'm not going to believe you.
So in your reconstruction, if you see something, how do you model it? And do you also look at the half maps to make sure that it's consistently there?
So the first thing I do is, does it make chemical sense? Does it agree with everything else? Is it interesting, right? If it's not interesting, I don't give it a lot of weight, and I come back to it. And it's got to make chemicals. I mean, I got my undergraduate in chemistry. It's got to make chemical sense to me. If it doesn't, then I don't care how good of a story spinner you are. You're violating the laws of nature, and then you might have a phenomenal story. It's just it's make believe. Now, I haven't seen anything like that, but that's how I go after it. And and if I don't know what it is, I don't model it. If I'm not sure, is that a water molecule? Is it calcium? Is it this or this? I don't model it, because I'd rather have an incomplete thing out there than have a wrong thing out there.
Sorry, it's going to be a little unrelated, but sure. But I guess kind of on the topic of modeling, have you been using any of these new AI sharpening tools for modeling? And would you put these maps in like a paper or something?
Okay, so yeah, there's, I think one of them called Deep EM Enhancer.
Yeah.
Yeah. So I have read stories where and then we're hearing more of this of hallucinations now. That if you don't train it properly, you're going to get something that looks like a protein, but it's not really your thing. So it's something to be careful of. So the program I use Phoenix's, I forget what the actual name of it is. But it improves the resolution, and it's not one of these deep learning based methods. It's based after the crystallography way in which you enhance resolution, and so it has less variables involved, and there's less room for hallucinations in being introduced. Now there is model bias involved, but if you do it properly, it's not that much of a problem. So yes, I built into this, I refine into this, and then when I'm done with my refinement, I refine against the original simply temperature factor sharpened map, and I say, do these two make sense? Or am I with the Phoenix algorithm, am I getting like a really high correlation coefficient? And when I look at the post-process map from Reliant, I'm getting something like a 52%, meaning that I've built into things that don't agree with the simply temperature factor sharpened map. So yeah.
I guess my comment was going to be, I think you're talking about the density modification.
Yes.
Yeah, in Phoenix.
Yeah.
There's like a cryo-EM function.
Yeah.
I guess I was going to ask a question about like, ethically, do people have issues with CryoSpark? Like people talk about CryoSpark overestimating resolution. There's also, I know that Shores is very pro like open science, and there's issues with like the CryoSpark not showing like all of their algorithms. Like, is that something that we should be concerned about, or is that something that we just take, like commercialization is good, so is that something we should just ignore?
Oh, you want my opinion?
Yeah. Anyone?
I don't have, well, look, here's the problem with me, is that I'm not a software developer. So I don't understand the problems that Shores sees and the problems that Shores communicate doesn't resonate with me as much because I don't have the understanding that he has. There's nothing, he's not being too sensitive, is what I'm saying. It's just I am too crude to understand the finer. I don't see what he sees. Like he might say, if everybody's not sharing, the field is not going to progress as fast. I'm like, I'm not sharing anything about the software development because I don't do anything. So I think for me to say that, oh no, everything CryoSpark is doing is fine, or I agree with Shares, I just don't know enough for me to say that my opinion should have any weight in this discussion.
And I also don't know, I don't know enough. I'm a beginner with CryoSpark, and obviously haven't seen its source code either.
So moving on to the topic of AI, as we talked about. So Fred, what do you think about some of the new machine learning and AI algorithms being applied, so like to most extreme, let's say tomography, the missing wedge, and trying to get that back and learning what that could be, to there have been something more benign, like, okay, you take a lot of images of noise, then you can do denoising, but then if you take enough images on a microscope, you could train a model to correct the aberrations of a microscope, and that'll be a very black box. So what do you think about the applications now of AI?
Yeah, well, the missing wedge reconstruction, that's scary to me, because that seems to me basically an application of knowledge of cell biology. That is, you see, say, part of a lipid vesicle, and you're just saying, okay, this has to be spherical, and so I'm going to put in a top and a bottom to it. That's scary to me. I haven't been. It looks impressive, but I have no experience with it. Let's see. Your second question was about something I was not going to be able to answer anyway. What was that?
Well, applications of AI, let's say, so some benign things are you take a lot of images of noise, then you can do a denoising to correct the micrograph. But then if you take enough images from a particular microscope or set of microscopes, you could potentially better model the aberrations coming from that microscope for correction.
Yeah, that makes sense. Of course, the noise that you're taking images of has to be some kind of specimen, like amorphous carbon. Otherwise, you're not going to see any aberrations. Sounds like a good idea.
Only if we had a machine learning group that could do that for us.
But you do.
Okay,
I mean, you
in
could
final
almost
minute-
convince Relion's local CTF and aberration estimation to do that.
Okay, we only have a couple of minutes left, so then I'll have each of our instructors impart any words of wisdom if they want to. So I'll let Fred go first, and then Reza can wrap up.
Well, I'm just amazed that any of this works. That's kind of the position where I'm at. And Reza can tell you much more about practical uses of these things. That's it.
I guess I'm really scared of this AI stuff, but I'll just leave it at that. And any words of wisdom, geez, I would say read a lot, read as many as manuscripts as you can. I know everyone's itching to jump in and look at their samples, solve their structure, write their manuscripts, but what I've seen is the people who are the most successful tend to also read the most and go into a project most ready rather than most eager. Make yourself ask experts all sorts of questions. Don't be shy about it, but do some research. Don't go in asking ridiculous questions, because then they're not going to want to listen to you a second time. And just be creative, and don't give up. I mean, I've seen a lot of challenging projects work out. Right? I've seen a project not work out in one group's hand, but then work out in another group's hand, because either they had some prior knowledge or because they went into it a little bit more prepared than the others. But being prepared, it's not fun. It's not fun, but that's how you win games.
Okay, so let's thank both Fred and Reza. Thanks so much. And I think we have a break before our cross-border practical.